Okay, this is the third hour of Physics 1C for May 18th, and we're going to keep talking about this LC circuit. We'll do a problem, and then we'll look at LRC circuits. Okay, so almost lost my train of thought of what we were talking about. Oh yeah, we were going to talk about the energy. How the energy transfers between these two objects. Okay, I'm going to try to draw a representation of how this is all going down, and then we'll look at the way that the book describes it. So our situation to begin with, so we're going to write up here t equal to 0. At t equal to 0, we have our circuit, which has a capacitor and an inductor. Like that right there. And we're going to look at this circuit at different time intervals. I feel like we need 5. Okay. So we've got our capacitor and our inductor. And we're going to look at what happens in our circuit. At t equal to 0, let's go up so we can see our charges. Q as a function of time is this. So at t equal to 0, and we're going to let phi equal to 0 too, so just ignore the phi. Q of 0 is Qmax, because cosine of 0 is 1. So at this time, what we have is the charge on our left capacitor plate is at Qmax. I'm going to basically let capital Q represent Qmax. Okay. And the other side of our capacitor has this, and then what's the current in the circuit at that time?
Zero.
Yep, 0. So we have all this energy in this electric field right here, and our current flowing through the circuit, I is equal to 0. If we go to a quarter of a period later, so if we go to t is equal to 1/4 of a period, so these are what we're going to have t over 4, t over 2, 3t over 4, and t equal to t. Period. So this is our cycle right here. So at t over 4 now, what's happening on our circuit is that the charge on the capacitor has now dropped to 0. So we can say up here that charge on the capacitor is 0, but the current flowing through our circuit is at a maximum. So now we can say that there is a maximum current, I, equal to I max. Now when this happens, when there's a maximum current flowing through here, there's also a magnetic field that's produced, right? And depending on how the coils are wound, the magnetic field is like something like, something like this. We'll just draw like a set of loops. So we've got a magnetic field. Oops, kind of made the direction wrong. And it's kind of flowing around like this. And it's to the right in the middle. So we've got our magnetic field here. Now, the current is at maximum, but was recently increasing, right? So if we think about it, the way that the current's working here, the current went from 0 to something, and the inductor has the effect of kind of wanting that current not to decay. So as the current tries to decay, the inductor is going to kind of keep the current flowing and prevent it from just stopping when it hits this capacitor plate. So eventually what happens then is that the charge on the right-hand plate ends up being positive Q, because we have current flowing into the right side of that. So at t over 2 there, we have the charge on the right plate is positive Q. The charge on the left plate is negative Q. But now the current has decreased, so the current has now dropped to 0, I should say. And this process basically repeats itself. The electric field now between the plates is going to point back the opposite direction. And now the charge is going to reach a maximum, and it's going to cause the current to flow back in the opposite direction. So now the current is going to be flowing this way. And that's going to be the maximum current at this point, which means you're going to set up a magnetic field pointing the opposite direction. So now our magnetic field is going to look like this. We'll have a field going like that, and then loops going around like this. So that's our magnetic field now. And then eventually we get back to our original picture, where we have the electric field pointing this way, and our charge on our plate looking like this. Plus Q minus Q. And then we just repeat, right? So you go from I equal to 0 to maximum to 0 to maximum. And in between these stages, you have both. You have charge and you have current. And in general, what happens is that in this position, all of the energy is stored in the capacitor. In the second position, all the energy is stored in the inductor. And then it just oscillates back and forth, right? Here you have all the energy in the capacitor. Here you have all of your energy in the inductor. Back to energy in the capacitor. Back to energy in the inductor. And it goes back and forth and back and forth. They just trade energy back and forth with each other. All right, so your book has this picture of this here, which goes, wait, where did it go? Did I delete it? Did I copy it and then not paste it back? I wonder if it's still on the clipboard. We'll find out. I don't think no, because I copied something else, right? Okay, let me grab it from the other sheet. Here we go. Didn't mean to do that. Copy. Back to here. There we go. Okay, let's read through their little picture right here. It's basically the same picture, but done much more professionally. Okay, so it says, in an oscillating LC circuit, the charge on the capacitor and the current into the inductor both vary sinusoidally with time. Energy is transferred between magnetic energy in the inductor and electrical energy in the capacitor. As in simple harmonic motion, the total energy remains constant. So here's their picture. The circuit's energy is all stored in the electric fields. T equal to 0 and T equal to big T. We close the switch at T. So there's our switch. Yeah, and they basically have a very similar picture, right? Where you start off with Q maximum, then you get the current. Capacitor's fully charged, 0 current. Capacitor, it's basically exactly the same picture, right? And that is our LC circuit. Anyone have any questions? By the way, you're going to see, so we said that the angular frequency in the circuit was equal to 1 over the square root of L times C, right? This is going to be referred to as the natural frequency of oscillation. The natural frequency. And one thing we can compare this to, as I was saying, is a mass on a spring. So in Physics 1A, you learn about a system where you take a mass, you put it onto a frictionless surface, and it has some equilibrium position that you call x equal to 0, and then you displace it, and what happens is that the mass basically oscillates back and forth and back and forth and back and forth, moving from a place where the spring is compressed, where all the energy is potential energy, back to a place where this mass is moving to the right, where all the energy is kinetic energy, and then it expands the spring to where you get all the energy back in the potential energy of the spring, and then the spring pulls the mass back to the left. So the mass basically is moving this way, and then it's moving this way, which means as it passes through this point right here, the equilibrium position, the mass will be moving either left or right with a positive Vmax or a negative Vmax. Well, I guess I should make the negative the ones on the left. So you either have a negative Vmax when it's going through the middle, or you have a positive Vmax when it passes through. This corresponds to maximum current, right? So in 2 of these positions, you have Imax. The other 2 positions, you have I equal to 0. The I equal to 0 occurs whenever the mass gets to here, and you have the spring is really compressed, basically. And at that time, you basically have a compression of the spring, which is defined like this, which you have like a negative Xmax over here. And when the box gets to this position, then the spring is like really, really stretched out when it gets over to here. And then this distance represents positive Xmax. So the compression of the spring is represented by, or is analogous to, the charge stored on the plates, and the kinetic energy or the velocity of the mass is consistent with or analogous to the current flowing, basically. Sorry, I went through this really quick down here. Did that make any sense to you all? How this compares to the what we call simple harmonic motion, or the simple harmonic oscillator? I'm gonna guess no. Sounds like no. Should I explain that better? What do you all think?
I think it makes sense.
Just have to read the textbook. Maybe. I mean, I can definitely explain this. The whole point of this is just to... Okay, I guess I should start off with this. Do you all understand kind of what's happening with the oscillations just within the circuit before we make the analogy?
Yeah.
Okay.
Yep.
So the analogy is just to say, imagine that the capacitor is like a spring that can store energy. Because it can store energy, right? And imagine that the electrons are like these masses, basically, that can slide back and forth and back and forth. So sometimes the electrons have velocity, which is when they have current. And sometimes the electrons are sitting still, which is when the current's zero. And the mass on a spring... I guess the thing that I'm neglecting here is you all might not remember this system as well as I'm hoping you do. Do you all remember studying this in Physics 1A?
Yeah.
Where you have this mass that oscillates back and forth and back and forth. And you remember that... maybe it's easier to just use a pendulum. I don't know. You remember that the mass basically... It has maximum energy when it's in the middle, which is maximum speed, and it has no speed on the ends because the box basically has to turn around because it goes back and forth and back and forth and back and forth. And it does so forever because there's no friction, right? This box would basically just go back and forth and back and forth. It would go forever, just exchanging energy with the spring, from spring energy to kinetic energy, right?
Yeah, this is acting as the electron.
Yeah, this is like what the electrons are doing in the circuit. And if we go back to this picture, this is what they're doing, right? Watch them. It goes right, and then it goes left, and then it goes back right again, reaching a maximum when it gets kind of like here. Now it's at maximum speed, and then it slows back down again. And then that's what they're doing, right? They're just going back and forth and back and forth. Just like a pendulum, right? Back and forth and back and forth and back and forth. We call that kind of motion simple harmonic motion. And the motion of the electrons in the circuit would be like simple harmonic motion, or at least their average motion, because the reality is that the electrons don't do this. They don't just go back and forth. They zigzag and bounce all over the place. This is the average motion that we're talking about when we talk about the current. On average, they're drifting left, or on average, they're drifting right. Okay, so the next thing to do, I guess, would be to solve a problem here. Maybe also to talk about this frequency piece of it right here. So look at what controls the frequency. The thing that controls the frequency is the size of the inductance and the size of the capacitance, right? So if these quantities were really small, what would happen to the frequency?
Increase a lot.
It'd be fast, right? Let's see if we can't do that in this circuit right here. Let's let this thing reach maximum charge and then open the switch. That's pretty much maximum charge because it was right around when the current was zero, right? I'm going to discharge this. In fact, let's just discharge this too. So what I'm going to do is we're going to increase the voltage of the battery just because. I'll go to 20 volts or something. I'm going to recharge my capacitor plate here. Boom, there it is. It's recharged. Whoops. Split junction. So now the only difference now is there's more charges there, right? And the last thing that I want to do now, I hope this doesn't change too many. Let's make these really small. The smallest I can make this is 0.05, so I decreased it by a factor of 2, right? And the smallest I can make this one is 10, so I can decrease it by a factor of 5. So how much did I change the quantity? 1 over root LC. I made this twice as small. I made this 5 times as small. So the quantity L times C I made basically 1/10 as big, right?
Yeah.
So then the frequency should be how much faster? Shouldn't it be like square root 10 faster?
Yeah.
Mm-hmm.
Okay, so that would be about 3, right? About 3 times faster? The square root 10 is like a little bit bigger than the square root of 9, which is 3, right? So it's going to be like 3.1 times faster. Let's see if that's true. Closing this. Yeah, they're going way faster, right? Look at the frequency, too. You can see it. Oops, let's zoom back out. I also increased the current, right, just to make the peak bigger. But you can tell the frequency is way faster, right? Really obvious. It also probably looks a lot more like simple harmonic motion. Would you all agree? Because you can really notice when these things speed up and when they slow down now. It's like, that's way faster. Then they slow down, and they whoop. So it's just back and forth and back and forth. That's what things do in these LC circuits. All right, so we can visualize how that happens. Can we explain why that happens? Let's see. So why would the frequency, the rate at which these charges bounce back and forth, why would it depend on these quantities? And why does it depend on the inverse of the quantities? Let's look at inductance first. Okay, so why would the frequency be bigger when the inductance is smaller? Why would that be the case?
I mean, I can only make like an analogy to like the.
That's
the
fine.
Analogy
is totally fine.
mechanics.
That's totally fine. So what does the inductance? What does the inductance represent? What's the analogy of the inductance in mechanics?
Mass. Inertia.
That's right. So if you're ever lost in understanding what inductance is, just treat it as if it increases the masses of the electrons. Okay. So this is like, so having a small inductance would be like having. Go ahead. You're going to explain it. Go ahead.
Having a small inductance is like having less mass. So, like in a spring, if we can imagine, like if we have like a really strong spring, and then if you have a really heavy mass on it, then it's gonna that spring is going to it's gonna have to really pull and push that mass. So
you get less acceleration for the size per mass.
Yeah,
right?
less acceleration.
It's going to be really sluggish, right? If you have a really heavy object and it's oscillating back and forth on a spring, it's going to be really slow. And then if you replace that heavy object with a tiny object, it's going to go really, really, really fast, basically. So that's what the inductance does, right? That's what you're saying, right?
Mm-hmm.
Just it applies that to the electrons. So now the electrons, if the inductance is small, it's like the electrons are really tiny, so they can move back and forth really fast, right? But if the inductance goes up, the size of the inductor goes up, now the electrons are going to be more sluggish with the way they move through the circuit, as if they got a bunch of extra mass. Okay. So hopefully that makes sense. What about the capacitance? Why does the capacitance show up down here? Why would the frequency increase if the capacitance becomes small? All of this understanding is really important for the next chapter. That's why I'm going through this, because we're going to want to take this understanding and expand it to AC circuits. Why would a small capacitance right here cause a high frequency? And why would a large capacitance cause a smaller frequency?
Doesn't the capacitance represent like the number of charges that can build up on those plates?
It does. That's right. Exactly.
So if the capacitance is smaller, then it fills up quicker, which means it can, like, the energy can go from the capacitor back to the inductor more frequently.
That's exactly right. That's very well put. Yep. If the capacitance is smaller, you can't store as many charges, so the current's going to reverse more quickly. And if the current reverses directions more quickly, that's exactly what we mean by the frequency. The frequency is basically the rate at which it oscillates back and forth, right? So if the capacitor gets smaller, then it's going to oscillate really, really fast because the capacitor's never really going to charge up, or it's going to charge up very quickly. However, if you replace the capacitor with a very large capacitor, now the current can basically just keep flowing and flowing into here. Let's see if we can do that. Let's just change the capacitance here. Let's wait till it reaches maximum, and I'll open it. We'll wait till there. Nope, that's not the switch. Right there. That's good enough, right? Let's discharge this. Okay, let's see what happens if we just increase the capacitance. Let's make it really big. And let's close it. Can you see that the charges are flowing way longer before they stop down? I mean, visually it looks full, but they're still flowing into it, which means it's not actually full. And why is that? Well, they can only do that if the capacitance is just straight up bigger. It is. And you can visually see that the frequency has changed, right? look at how much wider these peaks are. For the peak-to-peak width is much higher now, right? Much higher.
Mhm.
I wonder what happens if you change it while it's oscillating. Let's do that. Does it automatically go faster again? Yeah, kind of. You can see it right there. That it immediately changed. You can watch the way that the frequency changes right here. Do that, and now the frequency is going to grow. Now more, so the peak went up too because I did it while there was current flowing, so that kind of messes with it. But yeah, the frequency, if you don't remember, is like how spaced out these peaks are. Okay, good. So we have a physical understanding of why it depends on this, and a visual representation of it, as well as an analog, something we can think about to compare it to. So from here on out, when you think about a capacitor, you should kind of be thinking about a spring, and when you think about an inductor, you should be thinking about a mass. And to tie all this back together, does anyone remember what the angular frequency for, or the angular speed for this system was? Where you have a spring that has a constant of k and a mass m. Does anyone remember what it is? It's okay if you don't. It's square root of k over m.
The root k over oh.
Okay, you got it. You remembered it. That's good.
Yeah.
So these two are basically synonymous with each other, and you can see exactly how they compare. In fact, the mass shows up right here, right? Remember mass and inductance, those are compared to each other. So now we can actually compare the spring constant to C, right? The analog is that K basically is similar to 1 over C, the inverse of the capacitance. Think about that. When the capacitor is small, that's like a really strong spring, right? And that's consistent with what Kenny was saying too, which is if the capacitor is small, it can't really hold any charge, which means it's going to force the current backwards really quick, right? So a small capacitor is like a strong spring that when you try to compress it, it pushes back really hard on you, right? You guys see the analogy?
Yeah.
Okay.
That makes sense.
So there's like an inverse relationship here. Just keep that in mind as we're going forward. Okay, so capacitors getting a lot more interesting now. They were something that before could only hold charge, and now they can actually interact with the way that the current flows. You know, they can kind of redirect it in a way. Okay, so I believe I have a problem we can do with this over here. And then we'll, with whatever time we have left over, we'll talk about the LRC circuit. By the way, there is something that's a little bit unphysical about what's going on in this system, which is I think the reality is that if you actually hooked up something like this and you really did have superconducting wires, I'm pretty sure that energy would still radiate out of the system. Do you know what I mean? In the form of light waves, basically. I'm pretty sure that this couldn't happen forever. Because what did we learn in the previous chapters? We learned that changing electric fields produce changing magnetic fields, right? And we definitely have a changing electric field in between these plates. So it's going to produce a changing magnetic field which can propagate through space. I'm pretty sure that the textbook and me is leaving something out of what's happening in the system just because we haven't learned about it yet, basically. But in a couple chapters, we're going to learn about electromagnetic radiation in full. And I think if we look back at the system, we're going to realize that it's not possible for this to go on forever. You know, if it was, then you could create like a perpetual motion machine. Kind of. Anyway, so that's just a side note. Okay, oscillating circuit. A 300-volt DC power supply is used to charge a 25 microfarad capacitor. After the capacitor is fully charged, it is disconnected from the power supply and connected across a 10 millihenry inductor. The resistance in the circuit is negligible. Find the frequency and period of oscillation in the circuit. Find the capacitor charge and the circuit current 1.2 milliseconds after the inductor and capacitor are connected. Okay. So what we have in this problem is an EMF of 300 volts. We have a capacitor that is 25 microfarads and an inductor that is 10 millihenries. I'm just going to write that as 0.010 henries. And the resistance in the circuit is negligible. So there's no resistance. We want to find the frequency and period of oscillation of the circuit. That is really easy to do. To find the frequency of oscillation for the circuit, we can find omega, and omega is equal to 1 over the square root of L times C. So it's equal to 1 divided by the square root of 0.01 Henry. multiplied by C, capacitance. 25 microfarads would be 25 times 10 to the minus 6 farads, and we can use this to calculate omega. Your book, when you're doing your homework problems, just understand that sometimes this thing is sometimes called the natural frequency. So if they say find the natural frequency of oscillation, that's what they mean, okay? They may even mean 2 pi times or whatever. Okay, so this is going to be equal to looks like 2,000, yeah. So this is going to be in radians per second. Now, as you're doing your homework, you're going to have to be kind of careful because for whatever reason, we don't have a nice standard way we talk about this. We have different ways that we talk about this because when it says frequency, it might actually mean this quantity, f, and to get f, you just take omega and you divide by 2 pi, so you can get an answer that's just in hertz. So if we take 2,000 and we divide by 2 pi, that doesn't work. Divide pi. Then you get
1,000 pi.
What?
Just 1,000 pi, or 1,000 over pi. Yeah.
Oh, I see what you're saying. I got 318. This would be in hertz. So when the word is frequency, I think this is what they mean. And then period of oscillation, t, is equal to 1 divided by the frequency, or 2 pi over omega. So this is going to be that answer we just got, 318 to the negative 1. And so this is going to be 3.14. And the answer is going to be in seconds. Oh, wait. Times 10 to the negative 3 seconds. Or t is equal to 3.14 milliseconds. About pi milliseconds. It's probably exactly pi milliseconds, actually. Okay, so I think these are our actual answers. Just for when you're doing your homework and you're wondering what they're specifically wanting. That's part A. Okay, part B, find the capacitor charge and the circuit current 1.2 milliseconds after the inductor and capacitor are connected. So this is actually pretty complicated because we got to go back and think about everything that was said. So they told us that in this situation what we had was we had a capacitor and an inductor, and what happened was that the capacitor started off fully charged, right? So we know that this is our scenario at t equal to 0. We have maximum charge and 0 current, right? That's where we are. So if I want to find the capacitor charge and the circuit current 1.2 milliseconds after the inductor and capacitor are connected, I need to define my initial conditions. So our general equation for the charge as a function of time was that this was equal to Qmax multiplied by, I want to say, let's try cosine of omega t, and plus phi. I'm just going to say that this is probably going to work, and we'll just check. If I plug in t equal to 0 here, what do I get? Q of 0 is equal to what?
Qmax.
Just Qmax. Okay, is that consistent with the picture we have on the left?
Mm-hmm.
This is t equal to 0, by the way. I should have said that. Okay, so we're good. And that means that we should be able to use this equation to describe the capacitor charge at 1.2 milliseconds, okay? Now, 1.2 milliseconds is less than the period. So, in fact, it's what, about a third of the period or so? So we're going to be, if we look at our picture of how the plot worked right up here, if we're a third of the way, then we're going to be somewhere like in this region here. So the expectation I would have is that we're in the negative side of this. The charge is going to be negative at this point. Let's see what happens. Let's plug it in. So if I plug in Q of t, so t is going to be 1.2 milliseconds, is equal to Qmax. Oh, we didn't even calculate what Qmax is. We'll have to calculate that too. Times the cosine of omega. We found that already was 2,000. And then we need to plug in 1.2 milliseconds into here. And let's find Qmax. So what do we use to find Qmax? Well, we know these two. We know the EMF that was applied, and we know the capacitance, and the relationship is basically that the EMF multiplied by the capacitance is going to be equal to the Qmax. So Qmax is going to be 25 microfarads times 300 volts. So this is going to be 3 times 25 is 75, 7,500 microcoulombs. Is that right?
Yeah.
I think this is going to be about 7.5 millicoulombs. So let's write it like that. So we end up getting that Q of 1.2 milliseconds is equal to 7.5 millicoulombs times the cosine of all this stuff. And if we solve for this, what do we get? So if we do make sure your calculator's in radians for this one. Cosine of 2,000 times 1.2 times 10 to the minus 3. It is negative, and we multiply that times 7.5. So I end up getting negative 5.53 millicoulombs. You all agree? I'll give you a second to calculate that one. Do you all get the same answer? You got to convert this to seconds, but okay. And then the other thing we wanted to find was the current in the circuit after the inductor and capacitor. Okay, so to find the current, all we need to do now is to say, well, we knew what the charge on the circuit was, so we can find the current by taking the derivative of that. So I of t should be equal to negative Qmax times omega times the sine of omega t. And if we plug in our numbers, the current at 1.2 milliseconds should be equal to negative Qmax, so negative 7.5 millicoulombs, times omega, which was 2,000 radians per second. So coulombs per second, that'll give us current, and we do the sine of 2,000 radians per second times 1.2 milliseconds. And that should give us the current. What do you all get if you calculate this? So I got 10.1 amps.
I did too.
Does anyone have any questions? How are we doing on time? We got a little bit of time left. Everyone agree?
Yeah, I got that.
The numbers involved in this problem are kind of insane. I mean, millicoulombs is a lot of charge, and 10 amps is actually a huge amount of current. But, you know, I mean, it was a 300 volt source, so I think those numbers are reasonable. They are reasonable because it's a really big voltage source. So we started off with a lot of energy on our capacitor, and yeah. Okay, other kind of things that we can ask here is that you'll see show up in your problems. It might ask you to find, for example, the energy stored in the capacitor at this time. Just to remind you how you do that, if you need to find the energy stored in the capacitor, all you have to do is to take the charge squared and divide by 2c. And if they ask you to find the energy stored in the inductor, to find that, you just take 1/2 L times I squared. Very easy to do. But you'll definitely see this show up in your problems, you know, in the multi-step problems and stuff where they say, find the charge, find the current, just do a bunch of calculations. That's what you're going to see show up on these kind of problems. They aren't that hard, though, as long as you understand the concepts that are involved. Just involved, basically, in this case, we know an equation, and that equation relates the charge as a function of time, and we know how to get omega by using the components of the circuit. Okay. So the last topic for today, which is going to nicely lead into what we'll talk about next time, is LRC circuit. So the LRC circuit is exactly what you would expect. You have a resistor connected in series with an inductor, connected in series with a capacitor. And in this case, what we're going to do is exactly what we saw in the previous scenario, where we just start off with the capacitor having charge on it. So we're going to start off with, let's say this side of the capacitor is charged, and then we'll throw a switch in here and just close the switch at t equal to 0. So there's our switch. And what we're going to do is we are going to close the switch at t equal to 0. Now, we're not going to derive the solution for this one. It is quite a bit more complicated. We could write out what the differential equation is, I guess. If we do our loop rule like this, the current direction would eventually flow this way. So our loop rule would be something like negative IR minus L di dt, and then minus Q over C, and equal to 0. And then the next few steps for this would involve plugging in your i's with dq dt's. So you'd have, the first one would be negative, we're going to use the dots because I don't want to deal with this. This would be Q dot times R minus L di dt is Q double dot, and then minus Q over C. Well, there's your Q. So I think with differential equations, sometimes the way these are written is you basically kind of reorganize them with the highest power term first, the highest order derivative term first. I think something like this. Now this is...
Wouldn't the current be going in the opposite?
Oh yeah, it would. You're right. My bad. Yeah, it would. The current would flow up because it's going to flow away from this. Thanks. Anyway, this differential equation is kind of hard to solve. It's not unsolvable, like there is a solution to it, but I'm not going to go through the steps of how to solve it. Instead, what I'll do is I'll kind of show you what the answer looks like. Now, what's the main difference between this circuit and the circuit that we had before, the LC circuit? Because this is going to be a natural extension of what happens. So our LC circuit could basically have energy flow forever. And this circuit, that cannot happen. And why is that? Why can the yeah.
There's a resistor.
There's a resistor. That resistor is going to dissipate energy into the environment in the form of heat. So if I were to plot in my circuit right here, let's use our shape. If I were to plot the charge Q as a function of time, let me get rid, I don't need the other side of this, so we're just going to get rid of this piece right here. That way we can move off to the right again. Now what's going to happen is the charge as a function of time, it's going to start at a maximum. Whoops. It's a different color. The charge is going to start at a maximum here, which we're going to call positive Q. And the charge is going to kind of follow a sinusoidal pattern, except the difference is going to be that the sinusoidal pattern is going to decay over time. So I'm going to draw on here kind of a little guide for myself of an exponentially decaying envelope. And I'm going to draw on the other side too. So we went from there to there. So we're going to go something like here. Because what we now have to do is to combine the LC circuit with the RL circuit. The RL circuit had a current that did something like this, right? So when you add together the combination of a decaying current with an oscillating current, then what we're going to get is something that looks like this. Basically, a sinusoidal function whose amplitude just decreases over time until eventually it drops off to 0. So this is what the charge as a function of time is going to look like. The current as a function of time is going to be similar. Basically, the idea is that the energy in the circuit is going to slowly disappear. But nonetheless, before it completely disappears, the energy will pass back and forth and back and forth and back and forth within the system. And that's what the LRC circuit does. Does that make sense? That's how the LC circuit works. Okay. The only thing I'm going to leave you with here then is just to show you some of the results that you get from the textbook for this, because I don't think deriving or this is what the solution looks like right here. Okay.
Yeah.
And you can see that it has a lot of the same properties of what we learned before. So notice that there's a cosine function, and there is a new angular frequency. This is your new frequency right here, this whole big thing that's in square roots. I know it's hard to look at, but just imagine that that's a frequency. So you have cosine of something like omega times t plus phi. And what else do we have? Well, we have this term. And where did that term come from? That's basically the term that we got from the RL circuit, right? You've got your time constant right there, the R over L. There's a 2 that shows up, which, whatever, still basically, that's basically the same form of our decaying circuit, right? With the resistor and the inductor. So really it ends up being kind of a multiplication of our 2 different solutions that give us our answer. And then A again is just the maximum charge, right? So this is the angular frequency, this piece right here. If you have any problems with this in your homework, I can't remember if I assigned any. I think I may have assigned 1. Then just understand that this is what your angular frequency is now. And notice something here. If you look inside of how this angular frequency for the LRC circuit is defined, what do you get when you let R equal to 0? Well, you basically this piece right here on the right hand side disappears at that point, right? And you get back square root of L times C, 1 over LC. So yeah, when R is equal to 0, you get back the same thing we had before, and yeah, there you go. The LRC circuit is basically the analog to the LRC circuit for mechanics. Is you take this and you make it friction. You have a surface with friction, and all of a sudden, then it acts like a resistor, and it sends energy out of your system. So next time what we're going to be doing, if you want to read it for next time, we're going to be studying AC circuits and the oscillations that occur in AC circuits. The way that an AC circuit is going to work, just as a preview, is it's going to add a power source to the circuit that I just drew here. And that power source is going to drive current through the circuit so that this doesn't happen, so that the current doesn't decay out like this. Okay, so the only thing you need now to complete this is you put a power source in here. You make it so that the power force pushes left and right on the charges. That's what we call AC circuit, a power source that basically sends the current this way and then back and then this way and then back. And then we'll look at the response of each of these elements to that type of a flow of current. And yeah, that's